the endpoint. Well, this t is a slightly different t, but in any case, we wouldn't hold it fixed at the endpoint. So the question is, what if you did hold it fixed? So that means the class of variations against which the action is supposed to be an extremum is a smaller set. That's the only difference.
Okay.
So what would you get? So you might expect, well, I think it's almost, probably suggests what you should get. So if you require it to be, if you require the action to be extremum against all variations, then of course there's some equations that the curve has to satisfy. If you cut down the number of variations that go into that prescription, then you're putting fewer conditions on the solution, and so you expect to get more solutions. So this is just asking you what is the new class, the larger class of solutions that come out when you do that. Okay, any others? So we were going through the basic mathematical definition for the kinematics of relativity, namely the definition that we're ending. The definition that we had almost completed last time was that of manifolds. Remember, according to relativity, at least classical relativity, space-time is given by the differentiable manifold, and it also has under the causal structure. And we're going through now and giving precise meaning to those terms. So what is a differentiable manifold? And then what is the causal structure? But first of all, what is a manifold? If it's not necessarily a differentiable manifold, just a continuous manifold, or as it's sometimes called, a C0 manifold. That we had already defined that. I won't review that. We defined it in terms of the existence of an atlas, which is a set of charts such that the transition maps or gluing maps taking you from one chart to another in the set where the charts overlap have to be continuous. That's basically what the definition was. The other a remark I wanted to make was that another way to define a manifold is that it can be a certain kind of subset of a higher dimensional space. So that's very familiar to you if you think in terms of lower dimensional examples. So if you draw one dimensional manifold, which is basically a circle or a bunch of circles or a line, you think of it usually when you're drawing it, you're actually thinking of it as a subset of R2. Similarly, if you think of say a torus or something like this, then you think of it as a surface embedded in 3 dimensions. And it turns out that people have proved theorems that any manifold, let's say any compact manifold, any closed manifold, for simplicity, let's say compact without boundary, can be realized in the same way as a surface within a higher dimensional space. In general, in these cases, you just needed to go up 1 dimension in order to embed those manifolds. In general, you have to go up quite a bit more to get the exact number. I think it's like 2n plus 4. Anyway, but in general, you would be able, generically able to embed a 4-dimensional space-time in a 10-dimensional space, even getting the metric there. So that's another way of thinking them that makes them intuitive. And when we come to it aids your intuition, and of course we don't think of this embedding space as having any physical reality or any physical significance any more than we think of the coordinate systems that we put locally on the manifold as having physical significance. But it's a helpful way to think about them. And when we come to discuss tangent vectors, which will be just in a little bit, then what we'll define as tangent vectors will really be, with respect to such an embedding, which would now have to be a smooth embedding, they really will be tangents to that manifold, to that subspace. That's not the way we define them, but that's a possible way to define them. the other thing that I wanted to do was just give one last definition, which was that of isomorphism for continuous manifolds. So remember that the notion of isomorphism is a crucial one from the point of view of gravity, because it's the way that it's the one that allows us to make general covariance precise. So ultimately this will be diffeomorphism, but for now, since we're only dealing with continuous manifolds, it'll be a different class of isomorphism. It'll be called a homeomorphism. That's an isomorphism, technically speaking, in the category of continuous manifolds. It's the kind of isomorphism that's appropriate to continuous manifolds. And but to do that, so a homeomorphism will be as I said, you could also call it a C-dot isomorphism. And it's between two manifolds, or it can also be between a manifold and itself. And it's a map, F, from one manifold to the other, which preserves topology, basically. That technical way to say that is that the map is continuous, and it has an inverse. It's a one-to-one map of bijection, and its inverse is also continuous. So we just have to give that a meaning. So along the way, we'll also give a meaning to a continuous map. From one manifold to another. That'll be an ingredient. The definition of homeomorphism would follow immediately from that. And usually, so how do we do that? It's the usual story. We're in effect using the equivalence principle. We're saying that locally the manifold looks like a portion of a vector space, Minkowski space if you like, and then we transfer the concept, or we import the concept we're trying to define from the corresponding concept locally in the Minkowski space. So if we have a map from F from manifold 1 to manifold 2, and we want to know if it's continuous, we introduce a chart for each one. C2 saved to this, and C1 to this, taking its values in the vector spaces C2 and C1. And we also have, if we're interested in the isomorphism, we have F inverse going the other way. And we say that F alone is continuous if and only if C2, so F is continuous if and only if C2 circle F circle C1 is continuous. And then F is a homeomorphism if and only it has an inverse, and its inverse is also continuous.
Something's wrong with the compositions of those.
Oh, C1 inverse is that thing. Should be C1 inverse. So we go from here, and of course, I haven't written out all the fine print, but in general, you need many charts to cover the manifold, and so you really want to say within each chart where they overlap, it's continuous and so on. So basically, you would take any point x, x1 and m1, say, and x2 and m2, such that x2 is f of x1, then you would find a little neighborhood around this with a chart and a little neighborhood around this with a chart. And with respect to those, the chart maps, where the composition was actually defined, in other words, where the domains of the two charts overlap after you fold one over. Anyway, you can work. I don't think it's necessary to say in fine detail what's going on. You have the two manifolds, and you have here's one manifold, there's the other manifold. You have these domains of the charts, This, of course, might not map exactly onto this, but there'll be some common region containing the point in question. And in that region, you demand continuity. Or actually just enough to demand continuity at x. And that's one of x to homeomorphism. Okay, so that's a question came up last time. Someone mentioned it, pointed out afterwards that I hadn't actually defined the manifold as a topological space, and that's true. I haven't. One could easily do it from these things, but we don't need it as such. We just need to know what is a continuous manifold. Had we would define the topology of the manifold if we wanted to do it in the abstract sense, and to express it as an abstract topological space, we need to give neighborhoods of every point, and we would do that by importing the neighborhoods from the vector spaces. Someone also asked about how do we define continuous maps from one vector space to another. That can always be done, but the simplest way of doing it would be to say just put 4 coordinates on each vector space and let all the coordinate functions be continuous. If you're not familiar with the more general notion. Okay. So with that more or less completes the definition of C0 manifold. The next step is to go to the smooth case. So now we want to consider so remember we were going through this list of properties that space-time has, flat space-time and special relativity have. And the first one was to be a 4-dimensional space. In other words, it had a topology. The second one was to be a vector space. In other words, you know how to add vectors. Or you know what are straight lines and so on. That's called the linear structure. The third one was a symmetric, of course, and the fourth one was going to be its causal structure. So now we're going to the second one, which I think I call theta, which is the so-called differentiable or smooth structure. So we have to talk a little bit about smoothness. And when you have a smooth manifold, the concept that becomes available is a vector, or what's called, in the manifold context, if you want to be more precise, a tangent vector. In terms of the tangent vectors, that almost all the mathematical structures that go into general relativity are built up. So, in particular, tensors are built up from vectors. So remember, I should stop at this point. We're just almost going to repeat verbatim what we did for defining the continuous structure to define the smooth structure. So I should stop at this point and see if there are any questions about what we did when we defined continuous structure. Okay, so everything is clear. So what we did was we used the charts to transfer the topological structure from a vector space to, which might have been actually Rn, might have been a set of quadruples of real numbers. It might have been that. We used it to transfer that to the manifold. We're going to do exactly the same thing with a linear structure. Before we transfer the topology, now we're going to transfer the linear structure of the vector space, could be Minkowski space, to the space-time. But as I said, when I say the linear structure, that just means the thing that makes it a vector space. In particular, it's the thing that allows us to identify within the Minkowski space what is a straight line. So it allows you to formulate whatever it is called, the law of inertia, or Newton's first law, or whatever the relativistic name of it is, that particles not disturbed by anything else go in straight lines in space-time. So it's that linear structure that allows it, that statement to make sense. It's kind of a representation of inertia in this sense. But we can't, it's not so simple. There's a subtlety. In the case of the topology, as I think I stressed near the end of the last lecture, in the case of the topology, there's a finite region around every point in space-time that's structurally identical to a subset of Minkowski space. That is not true, of course, in a curved manifold. In order to have a linear structure, that's another name for that is being flat. Flat in the flat in one of the senses of the word flat. Not flat meaning that it has a metric flat, but just flat in the sense that it's planar in nature. It has notions of straight lines and parallelograms and so on. So we can't claim that in a curved space-time or in a curved surface like up there, we can't claim that in any finite neighborhood of a point things are flat. There's no exact definition of a straight line in a finite neighborhood, but there is in an infinitesimal neighborhood, and that's what it means to have a differentiable structure or a smooth structure. So, of course, the notion of infinitesimal neighborhood is not a precise one in mathematics. Just as a side comment, there is some branch of mathematics called non-standard analysis, which tries to make, or does in a certain way make sense of the notion of infinitesimal. It includes infinitesimal numbers and so on. Some people have used that as an approach to define tangent spaces. But it's not the traditional one, and it's by far not the simplest one, because if you want to make precise what are these infinitesimal numbers, you have to do a huge amount of work. So that was just a side comment, so we're not going to do that. We're going to represent infinitesimal numbers as we usually do in mathematics in terms of derivatives. That'll be the precise meaning. So what we want is that maps, we want our chart map, just as chart maps in the first case had to be continuous, in effect. That was our definition of continuity, but the way that it got made non-circular, of course, was the transition functions from one chart to another had to be continuous. Just as that they had to be continuous in that case, in this case they'll need to be linear in an infinitesimal neighborhood. And linear in so they have to look at a point like a linear map. And so from a modern point of view, that's the definition of differentiability. So what it means is that our chart maps will have to be differentiable. Now let me say a little bit about that, because it may not be so familiar to everyone. So what this is supposed to illustrate, this picture, is that a differentiable map is one that locally looks like a linear map. Okay. So think first of a map as some sort of function like this. You have maybe y as f of x, just some function. But what does it mean for the function to be differentiable? As you know, what it means geometrically is that it has a tangent, a well-defined tangent at every point. So to be differentiable at this point is to have a tangent at this point. But what is a tangent? A tangent is a straight line, and that's a linear map. And if I'm lucky, I can actually make it go through the origin. And that'll be actually, strictly speaking, a linear map. Otherwise, it's what's called an affine map. But basically, it means that about every point, there's a well-defined tangent vector. That there's therefore a well-defined linear map, this heavy one, that approximates to the actual function in the neighborhood of that point. So that's one way of defining what a differentiable map is. Now, what good is it? Why are we interested in this? Well, in a vector space, we can form displacements. And because So this is motivation. Displacements, that is to say, we can take the differences of 2 points as a vector. And then by doing that, we can we can have things like P of t plus this. Just think of special relativity again. These could be points in space-time, points along some world line of a particle. This could be some time parameter or just some parameter along the particle.
Hi there. Sorry to interrupt. Is it okay if your microphone's on?
Oh.
They're just not hearing you very well on the other end.
It's maybe not, but they are hearing? Oh, maybe just through that.
But it looks, there's a green light on the top right. It's on?
It's on. It says
on.
It says on. It sounds as battery red. It's on, yeah.
Okay. All right, thanks.
It just turned green. But I think there's no amplification here too. So.
Yeah, my microphone's out to the recorder. So they're not, there's something wrong with the microphone. So I'll just leave it be.
Hello? Is this any louder?
Not really. Sorry about that.
So it means it's not...
Yeah, you can put it down if you
I can put it down.
Yep.
Yeah, but that means it won't be recorded. So people who are following it will miss this. Okay, so you can form things like this. That means you can form velocity. If you take a limit, now you can form velocities. And then for velocities, you can differentiate them again. You can get accelerations and so on. You can take gradients of functions. That, in other words, it's what allows us to do calculus or analysis. And of course, most of the equations of physics are formulated in terms of those concepts. So if we're going to have any hope of writing down general relativistic generalizations of those equations, then we need to have a notion of derivative displacement so that we have a notion of this infinitesimal displacement in these. Yeah.
Does that say vector span or vector space?
Vector space.
Okay, that's it. That makes sense. Thank you.
Okay. Vector, it's a vector space. So let me give so now with all that background, all that talk about it, the definition is, of course, very simple. We'll just define a smooth manifold. That means a manifold in which you can form derivatives like this. Is just exactly like the definition before. It's given charts, but it has a distinguished set of charts. So it's a distinguished atlas, which is this distinguished set of atlases actually, because I wrote a distinguished atlas, such that all the transition maps are smooth. Okay. And I suppose I should have, smooth means, which I was just talking in words, that's just a synonym for differentiable. Then if you want to get into the minutiae of the definition, then there are different degrees of differentiability. There can be functions like this, which are differentiable once, but not differentiable twice, and so on. And there can be functions which are differentiable twice, but not 3 times. So for certain purposes, it's useful to consider those more general kinds of situations for technical reasons. But for most of this course, we can just assume that you have as many derivatives as you ever wanted. So say, or need, then you'll have as many as you need, which you can. So let's just assume that there's, in general, an infinite number of derivatives can be taken. So the technical definitions are C1. I mean, some family are called C1 and C3. So we'll usually assume that C infinity means that there's an infinite number of derivatives. This has. Oh, by the way, did I Did you want to ask a question? Cut off?
No.
Were you worked on this?
Now I am.
Now you do, yeah.
I just want to know what you meant by distinguished.
Oh, it means we select a particular atlas and say, this is the one you should use.
Okay.
There were a whole bunch of ones that were available. Now we're only limiting ourselves to special subsets of them. So we consider, another way of saying that distinguished is that it's regarded as part of the structure of the manifold itself. Just as we regarded that atlas as part of the definition of the manifold itself. In the continuous case, we do the same thing in this smooth case. So it has, another way of saying it is that it has an atlas, it's defined by the atlas just as before, but it has to be a special kind of atlas in order to define a smooth structure. And then to go along with that, we need another definition, a tighter definition of equivalence of atlas. Because remember, we said that equivalent atlases define the same manifold, given the point set at atlases on them. So we want to say that two, I won't, I'm writing this term. So remember, we defined two atlases, A and A prime, before to be equivalent when all the transition maps between the charts in one atlas and in the other atlas, they were also smooth. So the fancy way of saying that was that the union of the two atlases is an atlas. If you take all the charts and lump them together, it still makes an atlas. So now equivalence will be the same definition, except now we require that all the transition maps, just as we did here, to be smooth maps, not just continuous maps. Okay. So there can be. It's a bit of a subtle point. You can have a manifold. It could be a continuous manifold, like the sphere, for example, like is drawn up there. It could have an atlas that gives it a differentiable structure, and there could be another equivalent atlas that gives it the same differentiable structure. But you might find yet another atlas that also gives it a differentiable structure, but it's not the same differentiable structure. So that's a subtlety to sort of keep in mind. Now, I want to say a little bit about how we would define differentiability. Oh, by the way, I guess we can do that. So just as we define continuous maps from a manifold into another, we can define a smooth map from one manifold into another on exactly the same pattern. So I won't even bother to write it out again. It's exactly the same picture and so on, except where you see continuous there, now you see smooth. So it's smooth if only if all those maps C2, circle F, circle C1 inverse are smooth. And a smooth, but this is also the same definition, but the name is different. So a smooth isomorphism is called instead of a homeomorphism. I don't know where that name came from, but this is an obvious name. It's called, in analogy to homeomorphism, in analogy to homeomorphism, you say diffeomorphism. So that's the notion of equivalence that is in general covariance, and so that's why general covariance, since we're invariably dealing with smooth manifolds, general covariance is often called diffeomorphism invariance. And then I wanted to mention one special case, which will be important in a moment, of the smooth map from one manifold to another, which is a special case of a smooth curve in a manifold. This will be the central object when we come to define tangent vectors. So what is a curve? A curve is if you like, a one-dimensional subset of the manifold More precisely, we regard it as a parameterized subset or a moving point within the manifold. And that's a map from the real line, or sometimes an interval within the real line, but a map from the real line into the manifold. Okay. And so what does it mean for that curve to be smooth? Well, we gave the general definition. We have two if we think of this as this real line as itself a manifold, a one-dimensional manifold, then as a special case of a smooth map from one manifold to another, I can talk about a smooth curve. And if I plug in the definitions, what we're saying is that this was like M1 in the previous picture up there. This is like M2. To give this meaning, we now again need a chart. C, that's going to some C. That picture up there would suggest that we put a chart here, but we don't need to because, as I think I remarked last time, every vector space is its own chart. It just has a trivial chart, the identity map of it into itself. So what we're saying in this case is that the composition of this curve, this map gamma with this chart map C, should be smooth. So that's a smooth map of a real line into a vector space. So in other words, a smooth curve in a manifold is one such that its image under the chart, under any chart, is a smooth curve in the vector space. And in the vector space, we know what it means to be a smooth curve. Well, now I'm going to say a little more precisely what it means to be a I'm going to say it now. Well, what I was going to. Well, I'll just write it down what I said before. I'm not trying to actually do. I guess we're going to do that in a page. So, if you don't already know what the notion of a differentiable map of one vector space into another one is, we'll say a little more about it in detail in a moment, but to define a smooth map of V1 to V2 between vector spaces, we can, for example, use coordinates. So remember, which really means in this case, bases, right? The way to represent the point, the way to represent the point of a vector space, a vector in vector space, in terms of numbers, is to use to introduce a basis for the vector space, and then you just take the components of that vector and that basis, those are called its components, and it provides coordinates for the vector space. And then you're dealing with a map from numbers to numbers, or basically you would be dealing with a map in space-time case from R4 to R4. Right? And here you know the definition. This is just something you learn in, I think it's called multivariate calculus or something like that. You learn the definition of a differentiable map from one to the other in a continuous map. So I'll say some more about that as soon as we define vector, which will just be in a moment. But let's look at some examples of what we've been talking about. So let's think of some examples of one-dimensional manifolds, two-dimensional manifolds, three-dimensional, and so on. So here's an example of a one-dimensional manifold. There aren't too many interesting one-dimensional manifolds. Here's an example of one. It's a topological manifold, but you see the way I've drawn it, it's not particularly smooth. So I haven't, by the means of this drawing, given it some sort of differentiable structure or smooth structure. As I think I said, yes, smooth and differentiable are synonym. So this is meant to be a curve, like one of these kind of space-filling curves, which are not quite actually filling the space, but it's one of these curves, or like a curve of Brownian motion trajectory, which is continuous. There's no jumps in it, but it has no derivatives anywhere. It's not smooth. So those are both examples. So these are both examples of topological, or what I call C0 manifolds. C0, remember, was C0 was not in this list because it's not smooth at all. It's the obvious limit case of this list. Continuous, but not even differentiable. So these are topological, but they're not smooth. So what's a smooth one-dimensional manifold? There's basically only one. Of course, it can look like this. So I'm thinking of it as actually embedded in. Here I'm thinking of it as actually a subset of the plane, so we can indicate its smooth structure. So this is a smooth manifold. What about some one-dimensional objects that are not manifolds at all? So let me give one, and maybe you can suggest. Here's one. It's a figure 8. Two circles tangent to each other. Okay, it's almost a manifold, but it's not. Why is it not? Because there's one point that fails to have a neighborhood that looks like a subset of the real line. It's one point where there's one point that doesn't lie in any valid chart. And that's of course the point where they touch, because in the point where they touch, what it looks like is that locally like an X. It doesn't look like a line. In order to be a true manifold, it has to look like a line. So here's some more that are just like that. Just really a variation of the theme, except I made them not tangent in this case. Here's another one also. I couldn't come up with any very imaginative ideas of non-manifold in one dimension, except completely crazy things. Not even remotely resemble a manifold. And here's the one that's kind of a border case. Well, it's kind of border case. It's actually a pun to say that it's a boundary case, because this is really a manifold if you allow what are called manifolds with boundaries. So it's an interval, but it also has the endpoints of the interval. So these are non-manifolds. This is all of these, and this one is almost a manifold. In fact, in some more general notion, it's called a manifold with boundaries. But it didn't satisfy the strict definition I gave before, again, because you see there are special points. At the end point, it does look like a subset of the real line, but it doesn't have an open neighborhood that looks like a subset of the real. It looks like an open subset of the real line. Looks like a half-open subset of the real line. Okay, so that's one dimension. How about two dimensions? So again, an analogy with what we picture above. Here's a nice one, a cone. That's a topological manifold, but again, we haven't given it a smooth structure. We haven't defined what would be a smooth curve through this point. And in terms of this embedding, thinking of it as a subset now of R3, we haven't a nice tangent. We can't draw a nice tangent space to the manifold at that point. There are many spaces that you might regard as tangent, but there's no unique one. Nothing is coming into the decimal close to all the curves. Anyway, this one, there are some standard. Now we have two dimensions. There are 5 more. Both of these are smooth manifolds. So what is this? This dot, it's hard to show what the dot means. So the dot I mean, by the dot I mean this is a punctured sphere. So this is a sphere, but we're omitting one point from the sphere. So from a metric point of view, that looks a bit weird, but from a topological point of view, once you've taken one point out, like taking the North Pole out, you can, like the photographic projection, for example, you can open it out and make it into a plane. So it's topologically no different from a plane. That's a manifold, and it's also smooth, at least if we give it the differentiable structure suggested by this embedding diagram of the smooth manifold. Similarly, a torus, similarly, any Riemann surface, and even this so-called RP2, this non-orientable surface that you know it of 2 dimensions. I don't know. Are people familiar with that one? It's somewhat, I guess. What it is actually the sphere with antipodes identified. So that's the 2-dimensional smooth manifold. It's of interest for being not orientable, a topological property. So these are smooth again. And then what about this one is, as I said, isomorphic in the relevant category, in the relevant sense. For a continuous manifold, it's just the same as R2. And then here's a couple of non-manifolds of some interest. I'm not sure how to draw this. This is, so it's just a semicircle, including the interior. What this solid line is meant to show is that the boundary, this part of the boundary is present, and this dotted line is meant to show that this part of the boundary is absent. So this is, for quite a subtle reason, that it's not a manifold. Neither is it a manifold with boundary, because if you think about the neighborhood of this point, and you know the definition of manifold with boundary, it doesn't satisfy it. On the other hand, this is a manifold with boundary. So this is also a non-manifold, not even with boundary. And this is a manifold with boundary in 2 dimensions. Yep. I'm sure on analogy with this, you can think of many examples of things that are sort of 2-dimensional manifolds but fail at some point to be, they intersect themselves or something like that. This cone is an interesting case because as a continuous manifold, this is also, so it's homeomorphic to R2. But if we think of it as a differentiable manifold, it's not isomorphic to R2 in the relevant sense that it's not diffeomorphic to R2. In fact, it doesn't even have a well-defined smooth structure. Cases rather like these do come up actually in theory, especially when you're trying to do quantum field theory on space-time, that in one way or other it's forced to be singular or partly singular like this.
I have a question.
Yeah.
But is the cone infinitely long?
No, it really has a vertex.
But the base.
Oh, it goes on forever in this
Oh,
direction. Yes, sorry. Yeah, maybe I should draw it like this. It's meant to go on forever. You don't have to have it go on forever. You could cut it off, as the way I had drawn it originally suggested, and then it could be a manifold with boundary. And if I left out that circle that would have been the boundary, then it's again homeomorphic to R2. Because from a topological point of view, there's no distinction between.
if you kept it off though, couldn't it still be a manifold? It would just be homeomorphic to a sphere.
If I capped it off, yes, then it would be a sphere.
Oh.
It would be homeomorphic to sphere, and not, yeah, so if I did this, I don't know how to draw it. So this was present,
Mm-hmm.
yeah, then it would be homeomorphic to S2, and again, not diffeomorphic to S2. Because now it's got a singularity from that point of view here, and also here. I was just thinking of the difference between including this circle and not including this circle. If you leave this circle out, then it's R2 again. Okay. So let's think of some examples. 3 dimensions, it becomes already a mess to draw, especially for me. So I'll just give the name. So maybe I should ask. So what is, maybe you can think of some examples of 3 script to just use for, yeah.
Look, I wasn't going to answer your question.
Okay.
I was just going to ask, is it actually difficult to prove that the ones that weren't manifolds are not manifolds?
In general, it's not so easy to prove that things are not manifolds, right? It's much easier, if it is a manifold, it's much easier just to exhibit an atlas, and then you prove that it is a manifold. Yeah, so it's hard to prove that, because that's a special case of proving that 2 topological spaces are not isomorphic, really. That's, and how do you do that? You have to find some sort of invariant, or some property that it would have, that one space does have and the other one doesn't have. So in this case, well, in this case, for example, no, I can't. I was going to make. If I wanted to prove that globally this was not a circle, for example, so that's not quite the same question. But suppose I wanted to prove that this is not homeomorphic to this, or even to this one, because they're not homeomorphic. So then people have invented invariants that are very useful to do that, called homology groups and homotopy groups and so on. Basically what you would do in that case is you say, well, this has a curve in it that cannot be contracted to a point. And it has another curve that cannot be contracted to a point. But every curve that cannot be contracted to a point is in some way a combination of these 2 curves. So you could define what's called the first homotopy group, or sometimes it's called the fundamental group of the space. And you would see that it's the free product, as it's known, of those 2 of Z integers with itself. What that means is that every curve that's not contractible can be written by, you go around this, then maybe you go around this, then maybe you go twice around this, then you go around this backwards. Anyway, so in that case you could use what's called pi1 of the space, first homotopy group. Now if you look here, how many curves are there that are not contractible? You would see that there are far more, because there's a curve like this, there's another one like this. Basically, you just have the number of circles that you see here, and there's 4 or 5 circles, distinct circles. So pi1 of this space would be much more complicated. It'll have 5 generators. You'll need 5 generators instead of only 2 generators. That's the kind of thing that you do to prove topological spaces are not homeomorphic. Now, if you were to do this, if you were to take, I'm not sure, I have to think about it. If you wanted to show that, let's say you wanted to show that this one would be the simplest one, was not a manifold in the C0 sense. So that we'd have a point here. We claim that it contains, there's no chart that contains this point. That means, so we'd have to find an open neighborhood of this. So it would have to be something like this, which basically means it's just the same picture, but looking smaller. So we want to show that that chart, that little neighborhood that we've defined at that point, is not homeomorphic to any open set, any neighborhood of a point at the origin, let's say in R1. So how can you do that? So if there were a good chart, then there would be the origin, let's say. This point would be mapped to the origin. Here's a little neighborhood of the origin in R1. So you could see what's going to go wrong. You could map this bit down to here, and then this bit down to there. But then there's no place left to put this. So I think the statement is, so we have to look for a property that this has, that this does not have. And I think the property would probably, one property would be this. One way of saying it would be this. If you're here, then you can find neighborhoods, you can find arbitrarily small neighborhoods whose boundary, now we have to use the notion of boundary within R, but whose boundary points are just two, has only two. Right? So this neighborhood, if I ask, what is it? I mean, now I'm using another topological notion that we haven't defined, but this is just to give an indication. So here we have this interval here. Where is it? It has what's called a boundary within R. It's a subset of R. These are the points you can approach from within that neighborhood, within that red line, that are not actually, that either are not in it, or if they're in it, they're infinitesimally close to being out of it. So that means you can approach them from the other side. So what's called a boundary point is a point that has a neighborhood that contains both points in the set and points out of the set. So here we have precisely two boundary points. But here, every neighborhood that you could find, now we take a smaller neighborhood and ask within that neighborhood what are the boundary points. We'll see that there's always three of them. I didn't say it too clearly, but that's the basic idea, right? So every neighborhood, here every neighborhood will have a smaller neighborhood with exactly two boundary points within the first neighborhood. Here, that'll never happen. No, every neighborhood, if it has a sub-neighborhood, its boundary points within the first neighborhood will be at least three. So that's one way you could, I think you could prove it formally. But whether, besides giving this rigorous proof, when you try to make things rigorous in topology, you find that there's a lot of tricky definitions you have to assimilate first. But besides giving a rigorous proof, it should be intuitively obvious that no neighborhood of this looks like a neighborhood of a point in the real line.
I think you can make it rigorous with cutting points. So you're saying that they're locally homeomorphic, and so the real line, whenever you cut a point, you get two simply connected regions, and here there exists a cutting point that gives you three simply connected regions.
Okay, right, you can do that. Right. Then you have to define what's a connected.
There's more work that's involved in that.
Yeah, no, that's a good, right, that's uniquely good criteria. So generally you have to find some property that one space has and the other doesn't. Because it's pretty hard. You can't survey all the possible homeomorphisms. There are just too many, infinitely many of them. Okay, so I was asking for a definition of some three-dimensional manifold, and some suggestions for three-dimensional manifolds. Well, here's one that everyone looking for, so I'll mention. The three-sphere. Okay. How about some others? Doesn't have to be anything profound. True torus. True torus. Okay. So here's the true torus. What is a true torus? That's S1, the circle, plus S1, plus S1. Does everyone know what I mean when I write the product like this? The Cartesian product? Okay. So, this is also, in physics we use this one a lot. It's called, use it all the time, it's called a box with periodic boundary conditions. That's a three torus. Here's another one you won't know the name for. RP3, that's the analog of RP2, the non-orientable, simple non-orientable surface in two dimensions. That's the three-sphere. You write it like this, usually. It's the three-sphere modulo the two-element group. But it means we've made some identifications on the three-sphere, namely we've identified antipodally opposite points. An interesting topological fact is that this RP2, it's here somewhere. Oh, maybe I didn't actually write it down. Another one is RP2. This RP2 is not orientable, whereas RP3 is orientable. Okay, how about four-dimensional manifolds? Now we're getting to space-time itself. So how about what's the simplest four manifold you could possibly name?
R4.
R4. So this is the sort of model, the prototype for all of them, R4. And then of course we'll have analogs of the others. We'll have S4. This one wouldn't ever actually occur in classical relativity because you couldn't have a nice causal structure for it. But it's a fine manifold. Here's another way you can make manifolds, but you can take products. So here's one that will occur all the time. We just studied it in cosmology. This is R cross S3. So it's a parameterized family of S3s. This plays the role of time in those examples, and this is the role of space. And in fact, you can do the same thing with any three. So this 3 means that it's a 3 manifold. That's just indicating. So you can take any kind of spatial slice and build a cosmology out of it. And then the name for it is a manifold would be R cross M3, it's 3M. And also, in order to have a space-time, you'd want this to have a differentiable structure. So you'd make this a differentiable manifold, a smooth manifold, and R itself is a smooth manifold. And you'd have the product of 2 smooth manifolds.
So what's M3?
This is any 3 manifold. Let's say any three-dimensional manifold, say smooth 3 manifold. If you like, if you're doing cosmology, you'd probably want it to have either to be infinite without boundary with some device asymptotic. I mean, not too crazy topological topology. It could be just R3, and you would have R4. Or if it's to be spatially bounded, finite, then you want to normally take this to be what's called closed, which means compact without boundary. So no edge to space-time. It's only a finite volume, basically. Another example is S2 plus R2. So you can, any two things, you can product together any sets of manifolds whose dimensions add up to 4, and that would give you a 4 manifold. All these that I've written here are in a natural way both continuous manifolds and differentiable manifolds. And let's just, for fun, and also because it has physical application, let's look at some 5-dimensional manifolds. So, to those who might be familiar with Kaluza-Klein theories, what if I wanted to write down the simplest Kaluza-Klein spacetime? What do you think I would write down?
S cross R4?
Yes, R4 across S1. A circle across R4. So R4 could be, for example, Minkowski space. And then each point of space, in a Kaluza-Klein model, each point of space-time is actually a whole manifold. In the simplest case, a 5-dimensional case, it's just a circle. And that circle is the circle of phase that gives rise to electromagnetism. So Kaluza-Klein models are ones in which unify the electromagnetic field and the gravitational field. And they unify in the same way the gauge transformations with the diffeomorphisms, 4-dimensional diffeomorphisms. They do so in such a way that the gauge transformations become 5-dimensional, certain specialized 5-dimensional diffeomorphisms. So that's the kind of thing that occurs in Kaluza-Klein's view. We could take any one of these that might have been a 4-dimensional spacetime and product it with S1. That'll make it Kaluza-Klein space-time. Here's another one that everyone oops, I got the dimension wrong here. not for p equals 5, but here's one that comes up a lot, for example, in twistor theory, isn't it? So this is the set of light rays. Think of Minkowski space and think of the set of light rays in Minkowski space. So L is a ray, light ray, I should say, in M4. So here the point of the manifold is the light ray itself. This is something like what you do in whatever it's called, projective geometry, whatever it's called, where you treat simple subspaces as points. You dualize anyway, between points, between subspaces and points. But why is this a it's interesting to ask yourself, why is this a 5-dimensional manifold? It's even more interesting to ask yourself, how would I make a chart for this? But let's just ask, and how many charts would I need? But let's just ask, why is it 5 dimensions? So this is, well, to ask how many dimensions the manifold has is really just asking how many parameters do I need to specify a point uniquely in that manifold. So how many parameters do I need to specify a light ray? Well, so a light ray has a direction. Don't think 4-dimensionally now, think 3 plus 1 dimensionally. So it has a direction. Once you give its direction, its speed is already fixed. It's a light ray. It's a world line of a photon. So the direction is 2 parameters. Okay. But now we can ask, we know its direction, but that doesn't tell it because here's a light ray, here's another light ray going the same direction, that's another light ray going the other. Here's another one that's just following straight right after that, but it's behind it and so on. That's a different light ray, different photon world ray. So we need to not only tell what direction the light ray is going, but we need, that's called a photon. We need to tell where is the photon at t equals 0. Once you tell where the photon is at t equals 0 and you tell which direction it's going, then you've uniquely picked out its whole history, its whole world. So to tell where it is at t equals 0 is 3 more parameters. So that's why you need. That's why it's a 5-dimensional manifold. And finally, here's an example. Let's see what dimension it is. These are the wave functions in. Well, we can do it. Let's do it this way. These are the possible pure states of a qubit, as people like to say these days. In other words, it's the number of state vectors for a spin-and-a-half system. But we want to normalize them so that you always may as well normalize them. So what dimension of manifold is this? Well, let's count again. So psi is, so we always count, these dimensions are always counted in real language, not complex, or at least I'm doing it now in real language, not complex dimension. So what dimension is this? Is a real vector space. How many real numbers does it take to specify 2 complex numbers? 4. 4, right? So it's 4-dimensional, but now we've restricted it to say it's normalized, so it's 3-dimensional. So what is that? Well, I mean, this is obvious if you think about what the normalization means. It's just 4 numbers whose squares add up to 1, so it's a 3-sphere, right? But now if we take the pure states, what are called pure states, in this same quantum system, we lose another dimension because the phase becomes meaningless. We identify all those as the same phase. So it's what's called rays in the 2-dimensional Hilbert space. And in that case, it becomes 3-dimensional. So this one would have been S. I'm sorry. This would have been S3. But now it becomes 2-dimensional, and it becomes what is it? It's called CP1, But what's really is, it's just this two-sphere in this case. Right? So as everyone, I think most people are familiar that the two-sphere, the set of pure states of an electron, for example, forms a two-sphere because once you specify which direction the spin is up in, that specifies the state totally. And then there's a whole family of spaces like this. If we had taken C3 instead, then this would be 5-dimensional. It wouldn't be a sphere anymore, but it would be some 5D thing. And then it would be called C2 in this case, which would not be S2. Yeah. So you're familiar with a lot more manifolds, actually, than you might think.
I'm a little confused about the light ray being 5-dimensional. I mean, when you have just a path in 3 dimensions, I mean, you could say that a point on the path needs a direction, initial value, but usually you just parameterize it, but with one parameter, and it's one-dimensional.
It itself is one-dimensional. The path itself is one-dimensional. It's the space of all paths. It's the space of all light rays that's 5-dimensional.
Okay.
So that's the matter. I regard a light ray as an object.
Mm-hmm.
And now I want to say, how does suppose I have a family of light rays, I want to say, how does the frequency depend on the direction or something? Once it's derivative, so I ask you to differentiate. So abstractly, I have the space of all the light rays. Each one of them has a frequency. I've added information. I want to know the gradient of that frequency function on that manifold. That's like asking, how do I describe infinitesimal changes? The frequency with respect to infinitesimal changes in the light ray. So I'm not asking how many parameters does it take to parameterize the light ray, to select out one point in the light ray and another point in the light ray. I'm saying how many parameters does it take to select out the light ray from all other light rays. That's right. So the space of light rays is a 5-dimensional manifold whose elements are 1-dimensional manifolds. Just like R2 or something like that is a 2-dimensional manifold whose elements, namely points, are 0-dimensional manifolds. So if you were to ask how many parameterized light rays are there, then you get a sixth dimension. It would be that parameter along the light ray. And so that's about. Is there any more questions on that? That was just to. Yeah.
How is the magnitude of those vectors defined, those wave functions?
Oh, they're in Hilbert space, right? So they're in. I didn't go into all the. Because for physicists, it's sort of something that you see all the time. But if you like, when I say C2 here, that means I can just think of them as pairs of complex numbers. Z1, Z2, like that, where Z, they're complex numbers. And then the magnitude is just given by. And if I were to give these real coordinates, if I were to call this xi plus I, let's try k, xk plus I, yk, the k being 1 and 2. Then this would just be x1 squared plus y1 squared plus so it's just okay, so now that we can define, now we have defined, and know what we mean by smooth curve and so on, now we can do justice to vectors. So the next thing, I want to define vectors, or more technically what are called tangent vectors. As I said before, this is a fundamental concept for differential geometry and for relativity. So, and in particular, all tensors are built from vectors. And almost not, it's important to say almost, But almost everything that you deal with in relativity is a tensor of one sort or another. So in this way, the notion of vector is right at the center of things, at the basis of things. But what is a vector? What do we mean by a vector? Well, let's go back and think what is a vector intuitively back in flat space, where we say in a vector space, or say in Minkowski space specifically, which is not quite a vector space, but almost, because it doesn't have an origin attached to it. But in Minkowski space, what is a vector? So intuitively, a vector is given by a displacement. Right? We just have 2 points, P and Q, and this is how it's usually we learn it. The vector is just something that takes you from P to Q, an arrow from P to Q. So it's formally speaking of what you might call the difference of 2 points. However, in a manifold, of course, it's not flat in a finite region, just infinitesimally flat. As I kept saying, that's what it means to be differentiable. So we shouldn't be able to deal with displacement vectors in this generality. What we should be able to do is have infinitesimal displacement vectors. So we have the same picture, but we think of these as infinitesimally far apart. And then we call the vector that joins them u. So intuitively, a vector, so as we did before, I'm going to give some intuitive meaning of it, and then we'll go back and give the precise definition. So a tangent vector, which is what we're trying to define, a vector at a point P, is intuitively Q minus P, where Q is infinitesimally close to P, divided by some other infinitesimal to normalize it. So we don't want the vector itself to be infinitesimal C. So we normalize it in this way, which of course we'll formalize this by making it as a derivative. So this is the analog of thinking of a tangent vector for a curve like this. Right? You want the tangent to the point P. You find some other Q that's very, very close to it. You take this Q minus P, whatever you like to call it, say PQ, that vector. No, I call it Q minus P. So we take Q minus P, which is just almost straight, and then we divide by epsilon, so the distance between these, and we get the normalized tangent vector to the curve. So this is just the analog. That's all we're doing, but in higher dimension. So now we want to make, that's the intuitive idea. And let's work towards making that precise. So now we'll try to find, since infinitesimal displacements don't have meaning in themselves, but curves do have meaning, we'll try and find that curve whose tangent vector is the infinitesimal displacement, or the normalized infinitesimal displacement that we're interested in. So that's the strategy. So we have a point P and a point Q, just as before, or just as in that picture. We think of P being, we think of it as a point on this curve, and then this Q, maybe I won't call this Q. I mean, I could call it Q, but Q is also, so let's call P is equal to gamma of some lambda, and then let's call Q as gamma of lambda plus some infinitesimal d lambda. And then I'll take for epsilon d lambda, and then I'll apply this definition. And so then U will be Q minus d over epsilon. Then it'll be gamma of lambda plus d lambda minus gamma of lambda over d lambda. But this looks like the definition of a derivative. Indeed it is, trying to be that. So we'll just name it. We'll just name it as d gamma of lambda d lambda, which, using another common notation, I'll also call gamma dot of lambda. So these are just two different notations for the same thing. So once we figure out what this derivative means, that will be our definition of a vector. So just to summarize what we said, look at like, so this will be our tangent vector. Well, let's say it will be A. Let's say it better. It will be A tangent vector to M at where? At gamma of lambda. At the point which I call P here. So that's the intuitive idea. It's almost a definition. We just have to figure out what it really, how to give it, how to define it in a non-circular way. Because so far I don't know what it means to differentiate a curve in a manifold, only in a vector space. Of course, we'll use the same strategy, basically recurring to the equivalence principle and using transferring definitions by charts. So what we strictly, so what I'm going to do now is say, I'm going to turn things around and make this a definition. Given a curve, I'm going to say for every curve there's a tangent vector, and I'm just going to give it this name. And so I'll produce all the tangent vectors from curves. So therefore, I've got them all now. The only thing is I've got them too many times because two different curves can produce the same tangent vector. Two different curves which are tangent to each other will have the same tangent. So if this is a curve and this is another curve, and it's sort of infinitesimally, I guess I should, anyway, if they're tangent at P, then they're going to produce the same tangent vector. So I have to answer, to make this definition precise, so what I'm going to do then is I'm going to say that the tangent vector is an equivalence class of curves. That'll be the precise definition. All those curves that are tangent to each other define that tangent vector. They define a tangent vector. So is the strategy clear? Okay. So then I have to say when are two curves tangent, which is like asking what are these two tangent vectors equal for two different sizes of curves. Then I've defined the vectors, but I haven't told you how to. We like vectors because we can add and subtraction. That's the whole point of them. For example, you might like to express conservation of momentum or current or something like that. So you might say J1A plus J2A different currents. Or this could be momenta, for momenta, and so on. So most of the things you do with vectors require them to be added, subtracted, or multiplied by scalars. So the second question is how to add and subtract them. That really, in mathematical language, it says how to take these equivalence classes, these tangent vectors, and to actually make them into a vector space. And then the third one, which is kind of trivial compared to the other two, is how to rescale a vector. I'm just using the technical definition of a vector space, which is that its elements can be added and they can also be multiplied by a scalar. So if you have a vector, if you have two vectors, you know what their sum means. And if you have one vector, you know what pi over 3 times that vector means. So I'll just start now with at least the first answer. So the first answer is when are two curves tangent? Here we're really asking when do two curves define the same vector? And the answer was they define the same vector when they're tangent to each other. And so it gives meaning to that. We have to say what it means for two curves to be tangent. So let me give a definition. in defining tangent. So let gamma 1, no, it's gamma 1, be a curve, right? So under a map of the real line into manifold, it's a point, a moving point in the manifold described by some parameter intuitively. Let it be a smooth curve such that gamma of 0 equals p, then the second curve, gamma 2, is tangent to gamma 1 when we're at p. So imagining, of course, that gamma 2 also goes through p. So I'll imagine it. So I'll imagine that gamma 2 of 0 is also equal to p. So when is that true? Well, we're going to, it's the same strategy. If they're tangent in a chart, so if and only if in some chart they're tangent. So what does it mean to say that they're tangent curves in the chart? Well, in the chart, this equation actually has a meaning. It's just a derivative of the curve. It's a derivative of gamma lambda with respect to that. This is tangent in the vector space. So if and only if the derivative of c of gamma 1 of lambda, how many are there? Too many. The derivative of that with respect to lambda at lambda equals 0, which is where it goes through p. So it's like that picture there. This is lambda equals 0 here. Two curves through p, if it's equal to the same for 2, so dc of gamma 2 of lambda over d lambda at lambda equals 0. And this equality, both sides of the equation are vectors in the vector space that belongs to that chart. Okay. So these kind of things are kind of hard to take in on the run, on the fly, but if you go home and just read through it, it should become obvious. Now you might ask a question. Okay, you've defined it. You just said in some chart this should be true, but what if I take another chart? Maybe it won't be true. How do I know that this will be true in one chart if and only if? So to justify this definition fully, we have to go and check that it's actually independent of the choice of the chart. We'll do that later, or you can do it as an exercise. But let's assume that it's a good definition. And then when we have that, then this is just making precise what I said before. The tangent vector, or just called a vector, or most often you just say vector. After you get used to tangent vector. That's tangent vector at some point p in the manifold is a tangency class of curves gamma such that gamma of 0 equals p. By tangency class, of course, I mean an equivalence class with respect to the equivalence relation of tangency. In other words, if there's some vector in this tangency class, then every vector that's tangent to it is in the same class, and every vector that's not tangent to it is in some other class. So I assume that's a familiar notion. And then I'll just make a couple of final definitions. This is just a notation, really. The space of all tangent vectors at a given point P is called the tangent space to the manifold at the point P. And so it's the space of all tangent vectors to at P. And if we don't ask where it is, so we take the set of all vectors which are tangent anywhere in the manifold, that, which I could formally write like this, it's the union over all points of T, P, and M. That's called the tangent. You'll probably hear this a lot at some stage. Not in this course so much, but in other things. That's called the tangent bundle? I guess I have to say bundle, yeah. I'm thinking if there's any more colloquial, but it's called the tangent bundle, right? To the manifold there. And then the
Formally, that should be written as the disjoint union of those points. Because union, they're all embedded in
it's true.
the same.
Let me
dimensional
just put
space.
quotes there, I'm not going to do
Okay.
If I make P part of the definition, then sure, then it will be, I don't have to worry about that. That's right. So more important than that is the sort of picture of what's going on. So imagine a sphere. It looks like the same picture, but I'm thinking of it like a convex, two-dimensional object. So the tangent, you have to think of the tangent space. The tangent space at a point P to be just that plane, which is tangent to the surface of that point. And then at another point, and this is what makes the manifold case different from the vector space. At another point, it's a completely different plane in general. Only if this was flat would all the planes actually be able to be identified with each other in some way. Even then, they're not quite identified because the origin in this one is not the same as the origin in this one. But they're almost the same. But in general, these planes have nothing to do with each other. And that's a big headache. That's why it's impossible, say, to define in some simple way the total energy of some system, because there's an energy density, each one of those is a vector. But you can't add them all up in any meaningful way because they belong to different vector spaces. So let me just finish with this last definition. Again, this is just terminology. It's almost the same thing that I wrote before. If U is a vector in the tangent space to P, and gamma dot of 0 is U, then but it belongs to U, because now I've defined U to be formally an equivalence class. Oh no, sorry. And gamma, what am I saying? That's not even what I wrote here. What I really want to say is that I want to say gamma dot of 0 equals U. That really means that gamma is in the equivalence class U. The notation is confusing and ambiguous, but anyway. I'm going to sometimes use this infinitesimal method. Well, so this is the same thing that I just wrote. U is equal to D gamma D lambda. And lambda equals 0. It's just I'm messing this definition up. Let me just say it like this. And gamma is in the equivalence. So in this U, this is the equivalence. U regarded as equivalence. Then we write it this way: U is D gamma D lambda, which is I wrote. You also write gamma dot, and I'll also write D gamma of lambda is U D lambda. It would be useful to be able to write it in this form. So again, this is equating to infinitesimals, but I'll be using this notation. Okay. And we call if I didn't write this before, this is the last. We call U the tangent to gamma F. Okay, so that takes care. Let's see if there's any questions, we can take them now. Otherwise, the next time we'll now define addition for that. And then we'll come back and show that the definition that we gave there is actually self-consistent in the sense that that's independent of the chart we use. Yeah.
In the definition of two curves being tangent, do you need quality?
We need equality, yes. I think I must have covered that up. So here's the definition of two curves.
If they are proportional, since
If they're proportional, then they're not. Yeah. So that's a good point. So these are parameterized curves. So you could have two curves that were not tangent to each other by this definition, and you couldn't tell them apart when you drew them. So here it is. Yeah. So you could have a curve like this, and you could have a curve like this, exactly the same curve, and they wouldn't be tangent because, in terms of, if I draw lambda here, lambda might go 0, 1, 2, -1 like this, but the parameter on this curve should be 0 here, but it might be 1 here, 2, 3, 4, right? So if the parameter runs at a different rate, then it's not. That's a good point, because that's exactly, if you wanted to know how to define a multiple of the tangent vector, the simplest way is to use exactly the same curve, but change the rate at which the parameter runs. And that'll give you a multiple of the vector. So those will all be proportional to each other. If it's the same subset of the manifold, that curve, they'll all be proportional as vectors. They aren't necessarily equal. Yeah.
Is it proper to say unit speed curve and just restrict it to that, and we're okay?
It would be if we had a notion of unit speed.
I mean in a classical differential geometry sense.
That would mean that you'd have to have a notion of distance on the manifold.
Oh, that's true.
And we don't yet have that.
Okay, good point.
And then it would, if we did have it, that would be proper, but it would be ill-advised. Right?
Yeah.
Because you don't want to deal only with unit vectors in a vector space. You want all possible vectors.
Right.
So we could say those are the unit vectors, and then the other vectors are multiples. It's just as easy. In fact, it's easier to not put in that condition in the first place. Yeah.
So,
oh, you can relate. I know.
So here, when you define the smooth curve, you mentioned one chart. So if the definition of a smooth curve if you define it to be smooth for all charts, then does that force the manifold itself to be smooth?
I think if there are curves, yeah. So if you said that, if you get the definition that the way you said, that a curve is smooth if and only if in every chart it looks smooth. Mm-hmm. But you had put no condition on the atlas. Mm-hmm. And now I think, I'm not sure of this, but I think, two things could happen. It could be, okay, that's a good definition, now show me a smooth curve. There aren't any, right? There's no smooth curve at all. Because it looks smooth in that chart, but it doesn't look smooth in this chart. So in general, that's what would happen. But now if you put a further requirement, you said, now I want it to be the case that through every point, there's at least n independent smooth curves where n is the dimension of the manifold. You'd be pretty close to requiring it to be a differentiable manifold. Mm-hmm. I don't know exactly how close you'd be, but you'd be quite close to it. In fact, if you said that there was a smooth scalar field at every point, and enough of them, you'd be even closer to that. Because that would be secretly like saying you have enough independent coordinate functions to make a chart, to build a chart.
No, but if you were to say there exists one chart so that such that the curve is smooth, then what? And then you don't put any condition on the manifold itself. Would you run into problems later on?
You wouldn't have you wouldn't have smooth. You'd run into problems right away. You wouldn't have enough smooth curves. So it might happen that the tangent space would just be empty, or it would just be the zero vector or something like that. The zero vector will always be. I mean, the vector that doesn't, the one that goes at zero speed, that's going at zero speed for everyone. Right? So you might have the zero vector, but you wouldn't get. What we need is for the tangent vector to have an equal dimensionality to the manifold itself. So you want the manifold to be locally in an infinitesimal neighborhood flat of the same dimension. I mean, it has whatever dimension it has. So if we demand it to be flat in an infinitesimal neighborhood, we're demanding in 4 dimensions that there be 4 linearly independent tangent vectors. And there wouldn't be. I mean, in general, it wouldn't be without extra requirements. But you might, I mean, this might be another way of constructing the idea of tangent space. I don't think this is necessarily, as I said once before, it's not the most intrinsic, but it's the most convenient, the quickest way that I know to get. And it makes I mean, since it uses the equivalence principle in some sense, it makes contact with the physics in a nice way. But there might be other mathematically sleeker ways of doing it. Any other questions? Okay, so next time we'll define addition and then go on to the method.